Go ahead and get started. So you need some notes out because we're going to write some stuff down. We are starting a unit. I don't know if this is 4 or 7 or 23, whatever. We're going to start a new unit. This unit's got some other terms in it, but I'm just going to call it for now Newton's first and second law 2.0. Okay? Have you ever had an opportunity where you've gone to the store to buy, I don't know, toothpaste or shampoo or whatever, and you go in knowing that you need to find the blue box or the yellow bottle or whatever, and you walk in and the bottle isn't the same, but it says the same great product, just a new box or whatever, you know what I'm saying? Okay, that's exactly what we're doing today, okay? Unit 4, I think this is unit 4, is the same thing as we've already done, just in new packaging. That's all it is, okay? You know this stuff already. There's going to be one thing that I'm going to throw at you, but I'm not going to throw it at you today. So today, this is just new packaging of the same stuff. So Newton's first and second law, we've talked about that a while ago. We got to know and love it. And we said, do you remember that if an object has a net force of 0, then its acceleration is 0. And if an object has a net force that isn't 0, then the acceleration isn't 0. And the big piece of that there is that the acceleration of the object, if it's accelerating, the acceleration is equal to what divided by what? Yeah. So that's all well and good. We know that. We love that. We get it. Okay? I'm going to do something wild and crazy. Are you excited? Yes. Okay. Here we go. I'm going to multiply by m. Whoa. I know, right? It's pretty exciting. I'm going to multiply by m on both sides. I'm not going to divide by a, but that was a good idea. I know. So now I'm going to multiply by m. Now I am going to do something with a, though. I'm not going to divide by a because I actually want to do one other thing. I want to use what I know a is. What is acceleration? Physically, what is it?
F net over m.
A change in velocity over time, right? So instead of writing a as just a, I'm going to write it as a change in velocity over time. So now if I break this all down, I've got an m out here, and that's equal to F net. How are we doing? Same stuff, new packaging, right? So now I'm going to do one more thing because I don't like denominators. I say I want to get rid of the denominator. So now I'm going to multiply by t. Woo! That's a fun t. My t's are going to go away. And I'm left with m delta v is equal to F net times t. Now I'm going to put a big box around it. What? There it is. That is the new packaging that Newton's first and second law has in this unit. Okay? Really not big and scary, but what can we do with it? Glad you asked. They change some words and they make things new and different. This quantity, F net times t, a new word, a new term for this. F net times t is also known as impulse. Impulse, okay? You've heard the word impulse before, perhaps not in a physics context, but have you ever heard of or thought about the idea of impulse purchases? Okay? Yes. If you have ever... That is me. So this unit is for you, right? Okay. So if you ever go to, pick your store, right? You go to Target, you go to Walgreens, you go wherever, and you have this list of things, or you have an idea of what you're going to get, and then as you're walking towards the cash register, they have all of that stuff, right? They have chapstick, they have gum, they have batteries, they have this and that and the other things that you did not intend to get, but you're totally going to get. It's so convenient, right? There are people that are marketing people who focus on impulse purchasing, right? They market for Kate and for the rest of us too, because we got to admit that we all do this, right? Now and then, for sure. What does an impulse mean? It means, oh, go ahead. Did you want to say something? You sure? Okay. All right. An impulse literally is where you're feeling some sort of force. Something is drawing this to you over some amount of time, right? That's literally what it means. An impulse is a force acting over a time. And hey, let's look at the other side because we can find out what it does. It causes you to change your
mass.
What's the changing thing? Change your velocity, right? You're walking towards the cash register. I'm out of here, and then you're like, oh, I see this thing, right? And so you were going this way, now you're going this way, so you changed your velocity, right? It's the same mass until you start eating all those Snickers bars that you buy, right? But that's a whole different issue, okay? An impulse is changing your velocity, and it's changing this other quantity here. I don't know if you guys have ever seen this quantity, m times v. Does anybody know what that is? Mass times velocity. Anybody know what that is? Niam does. She's looking at me funny.
Newton's first law of physics.
What is it? It's your momentum, yeah. Okay. An impulse causes a change in an object's momentum. Okay? Momentum is an object's mass times velocity. Why did we have to come up with a new quantity that's mass times velocity? I don't know. The short answer of it is literally because interesting things happen when you multiply a mass times a velocity. That's it. There's nothing magical about mass times velocity. In fact, the units of mass times velocity literally are just kilograms times meters per second. Like there's nothing fancy about it. It's just a quantity, mass times velocity, and we call it momentum because we needed something else to call it. Okay? And an impulse causes a change in an object's momentum. Now, to me, this thing in a box is really just Newton's first and second law, but they give it another name too. This is also called the impulse. Oops, come on. Momentum theorem. The impulse-momentum theorem. Okay? I did it 3 times. Yeah, it's true. So, what? It's a silent P.
There's a P on it?
Yeah. Oh, yeah.
That's like.
Why not? You've been told wrong.
Is that how it's supposed to be spelled?
Yeah. Come on, you guys. Come on. No. So momentum is changed by an impulse. So if a force acts over some amount of time, then the mass times velocity changes. Now, the funny thing about this, and probably the reason that they gave it its own name of the impulse-momentum theorem is because there are a couple of different ways that you can change momentum. You can either have a really big force that acts really fast. Think of like a tennis ball being thrown at a wall. Its velocity is going that way, right? The wall hits it, and holy cow, it starts moving this way. You with me? Its momentum changed because its velocity is going the other way now. It was a big force over a very, very short amount of time. Another option would be to have a really, really small force that acts over a really long time. The game is that in a lot of cases, it's better to act over a longer time to minimize the force. Okay? Case in point. If I asked somebody, I'm just trying to check the time here. If I asked somebody, I'm not going to do it because we don't have a lot of time, but we'll do it maybe another day, to come stand up here on this table. Okay? No, not right now, because you're going to beep again in a minute. So from here, and I asked you to jump down. Let's think about good choices and bad choices in terms of jumping down. Once you step off of this table, what's going to happen to you? You're going to fall, right? You're going to accelerate downwards, and by the time you reach the floor, you're going to be going pretty fast, right? So you've got some momentum. You've got your mass times the velocity when you reach the floor. And the floor is going to do what to you? It's going to stop you. It's going to apply a force. It's going to have an impulse, right? Now, if you jump and lock your knees, Kian is making a really nasty face. Why? It's gonna hurt because that force is gonna shock your knees, and it will hurt. But what would you do instead, Kian? What's the better choice? To bend your knees. Why?
It evenly displaces the force across your body.
Not quite. What does it increase?
Time.
It increases the time over which. That was awesome. It increases the time over which the force of the floor pushing up on you acts. Are you with me there? By increasing the time, we can have a smaller force for the same change in momentum. How are we doing? We okay? Yeah? We got 3 more minutes. Hot diggity. Let's take a look. All right. No, let's not do that one. Let's do this one. All right. Take a look up here real quick. Cars moving along horizontal roads are about to be stopped by a protective barrier. That's fun. All the cars are the same size and shape, but they are moving at different speeds and have different masses. The barriers are all identical and exert the same constant force. Rank the time it takes to stop the cars as the barriers apply the same constant force. How are you going to approach this question? You want to talk to your table mates real quick?
Yeah.
Sure, do it.
E is greater than A equals C is greater than B. 3.
E is greater than C is equal to A. C, right? Yeah.
I know what Brian said.
Yeah.
How'd we do?
Especially if you're moving at 20 meters per second.
What's that?
I hope that's just a dummy. Because
I know, right?
if you're
Crash
moving
test. It's all about impulse. Impulse-momentum theorem every single time. Do we get a rank? Rank the time it takes. So you've got M. Oops, yep, there we go. Delta V is equal to F times T. So the F net is going to be the same, right? We're ranking the time, so what do you need to do? Divide by F? But it's the same F, so we really don't care about the F. What do we need to do to get them ranked? Multiply mass times velocity? Yeah. We get an answer? Oh. Go.
It's D and then B, or A equals C and then B.
Hey, let me tell you really quickly, if you wrote down that homework, that I got rid of 2 of them. So chapter 9, question 4, and problems 1, 3, and 9.
Is this on the?
I will put it up on Canvas in just a sec. Yes. Is that what you're asking?
No, we're not gonna have it.
Is there a calendar?
We voted against
Yes, there is. Like, it's not on assignments, but there's a calendar posted. Yes, like where they have been. Yeah.
I go for the